So let's look now at a permutation. And we're going to use permutation to solve problems with distinguishable objects. And what that means is objects we can tell the difference apart. So a permutation is really just an arrangement of a set of elements in which the order is important. And that is important. The order of the elements is important. We're going to look at permutations that have distinguishable objects, objects that are all different, and indistinguishable, some are the same. And what a permutation really is just the fundamental counting principle put into a formula. So we're going to develop a formula to do more complex problems, which are really just extensions of the fundamental counting principle. So if we have distinguishable objects, objects that are different, and we want to figure out the number of permutations where order matters, if we have n distinct objects, then the number of permutations is n factorial. So if we had 4 different color cubes, and they're all distinguishable, the number of ways we can arrange them, well, if you think fundamental counting principle, it was 4 times 3 times 2 times 1, which is really just 4 factorial. So if we arrange all of the objects, all n of the objects, then the number of permutations is just n factorial. So let's put this into practice. 6 friends go watch a movie together. How many ways can they all sit together? Well, if we did this with the fundamental counting principle, again, we have 6 different seats for 6 different people. The first seat, there are 6 people that could take that first seat. That means 5 for the second, 4 for the third, 3, 2, 1. Fundamental counting principle tells us that we'd multiply those all together. But remember, that's just the same as 6 factorial. So we don't need to use the fundamental counting principle. We can, but either way, we're going to get 720 different ways those people can all sit together. Well, let's make it a little more complex. What if these 6 friends go to a movie, but now Tabitha must sit next to John? So they want to be together. Well, what we consider in this case is we put Tabitha and John, and we consider them one object now. They are one object together. So we're going to say that Tabitha and John are one object, and that means there are 4 other friends. So if we were arranging these, we would have 5 factorial ways that they could be arranged. But we have to be careful here, because Tabitha and John could sit like that, left and right, but they also could be considered John and Tabitha. So if we consider John and Tabitha, John on the left and Tabitha on the right, we actually have to consider that there are 2 ways that this can be arranged. So it's not just our 5 factorial from our objects, but it's 5 factorial multiplied by 2. One way is Tabitha then John, the other way is John then Tabitha. And when we do this calculation, we'll get 240. Well, that's if Tabitha and John sit together. What if we want the scenario where they do not sit next to one another? Now, this can be a very complex calculation, but we have to consider what the possibilities are. So our total possibilities are only one of 2 scenarios. We either have Tabitha and John sitting side by side, or it's either going to be Tabitha and John not sitting beside one another. So they're heartbroken because they're not beside one another. That's the only 2 scenarios that can occur. They're either going to be beside each other or not beside one another. And what we're trying to find is what happens if they're not together. Well, we've already found the total from example 1. There was 720 possible ways that all of the friends could sit together. Now, we calculated Tabitha and John sitting side by side. There was 240 ways, and we want to find the other which I'm just going to call x. So now it's just simple algebra. Our x value of Tabitha and John not together is just 720 minus 240, which gives us a total of 480 different ways they could not sit together. So much easier calculation if we consider that the only possibilities are Tabitha and John together or Tabitha and John apart, and that would give us our total. Well, let's consider this scenario. What if 6 friends go to watch a movie, but there are only 4 seats? How many ways can they be seated? Now, we're not choosing all the friends, so we're not taking n factorial, or in this case 6 factorial. We have to consider the fundamental counting principle. We have 4 seats available. The first seat, one of the 6 friends can go in there. Then there's 5 that remain, and 4 and 3. And we could do that calculation and figure out what that number is. But we're going to take this scenario and imagine that we did extend this down to 1, 2 and 1. That would allow us to write 6 factorial in the numerator. Well, what would the denominator have to be to keep this the same value? Well, we would just have to put a 2 and a 1 in the denominator, which would mean we have 2 factorial. Well, it's pretty easy to see the 6 comes from the 6 friends, but the 2 in the denominator, and this is the important piece, the 2 is going to come from the 6 friends minus the 4 seats, the number of options that are available. 6 minus 4 is 2. And this little scenario is going to allow us to create an equation for permutations. And this is an equation where not all of the objects are arranged. We have n possible arrangements, but we only take r of them. In this case, we can use this new formula, NPR. N represents the number of possibilities. R is the number that are picked. And it's P because order matters. It's a permutation. We sometimes write it in this notation, N comma R. And all this is just this calculation. N factorial divided by N minus R factorial, where N is the number of objects, but there's only R spaces that are picked or orders are available. Now that's going to become very important as we do calculations. So let's try one. We have a 4-digit combination and we want to create a combo with no repeats using the numbers 0 through 9. So in this case, we have 10 distinct objects, or in this case, digits, to choose from. And we want to choose a code that has 4 digits. Because it is a combination, 4-digit combination, we know that order matters. So we are going to consider NPR. But anytime we do these questions, we always have to ask ourselves, does order matter? And if order matters, especially in a combination, if you don't put those digits in the right order, you're not going to crack the combo. Order does matter in this case. So order matters in this situation. So we can use our NPR equation, which is n factorial over n minus r factorial. Well, that means we're doing 10p4, which is really just 10 factorial over 10 minus 4 factorial, which is 10 factorial over 6 factorial, which if we expand out the larger, 10 times 9 times 8 times 7 times 6 factorial, all over 6 factorial. The 6 factorials cancel out, and we just figure out what 10 times 9 times 8 times 7 is, and we get a value of 5040. 5,040 different combinations. And that's what we would do if we're not going to use every single digit. And the other important piece is we have no repeats. They are distinguishable objects. We're going to look at more examples like this in class.